Hello everyone. Welcome to the Yavar Colloquium. I would like to introduce Yavar Kian, who is from Marseille University. He'll be telling us about the Calderón problem for quasi-linear conductivities. Over to you.
Okay, thank you very much for the invitation. It's a pleasure to be here. So it's my first talk to a city in India, given into a city in India. It's a pleasure to see that there's an active community on inverse problems here. So as you can see, the title of this talk is the Calderón problem for quasi-linear conductivities. And through this talk, I will try to clarify this different notion that appears in this title, including this idea of Calderón problem and the quasi-linear conductivities that we will associate with this type of problem. Okay, so what I would like to say also is that this talk is based on some joint work with Catalin Carstea, Feizmohammadi, Katya, Krupchyk, and Gunther. So before we move to the statement of our problem, I will say a few words about the notion of inverse problems, which is strongly connected to this so-called Calderón problem. And for that, I would start with an introduction to this idea of inverse problem. In order to understand the idea of inverse problem, you need to first consider the notion of forward problem. So for forward problem, you start with a system from which you deduce the response of the system. In the mathematical framework, you can associate the notion of system with the one of partial differential equation and the notion of response of the system to the one of the solutions of these equations. So at some point, the idea of forward problem is that you have an equation, you solve it. For inverse problems, the situation is different in the sense that you do not have a full knowledge of your system. So you have a system with some unknown parameters. To this system with the unknown parameters, we add some partial information about the response of the system that we call observation or measurement. And the goal of inverse problems is to combine all this information in order this time to determine the system. What is unknown here is the system, or at least the unknown parameter in the system. What remains here in this description is actually to give a meaning to this word determine. And through the theoretical study of inverse problems, we will give three different meanings to this word that I will describe below by associating systematically the notion of system with the one of equation and the notion of response of the system to the one of solution of the equation. The first meaning that we give to this word determine is the uniqueness. So the idea of uniqueness is to describe this determination through some injectivity properties, saying that if the measurement or the observation for two systems coincide, then the two systems coincide. So here, this injectivity properties is described through this implication, saying that if two measurements for two different systems or two different equations coincide, then the unknown parameter coincide, and by the same way, the two equations coincide. The second meaning that we give to this word determine is the stability, where this time we want to add to the uniqueness properties some continuity properties. And the idea is not to prove the stability result through a step-by-step process starting with the uniqueness, but to showing instead a stability estimate, which consists in an estimate of the difference of the unknown parameter by a function f that we take at the difference of the measurement, while this function f will be equal to 0 at 0, which of course guarantees the uniqueness. Finally, the last meaning that we give to this word determine is the reconstruction, where the idea this time is to fully reconstruct the unknown parameter from our observations. Okay, so this is a quick introduction to this notion of inverse problems. What I would like to say also is that this class of problem has many applications, including applications in medical imaging, seismology, problem of environment. And beside that, what we should think of is that we are often considering inverse problems through questions like where these lights come from or where these sounds come from. These questions are actually inverse problems. So now let us move to our own problem. And I will start with the statement of our problem, for which we will consider first omega to be an open-bounded subset of Rn, n being bigger than 3. And on this domain omega, we will consider the following boundary value problem. So this boundary value problem is an elliptic, contains an elliptic equations Here you have the divergence, and here you have the gradient. And in between, you will have a conductivity, depending on the space variable, the solution, and the gradient with respect to the space variable of the solution. So this equation is considered on the domain omega, and we add to this equation the following Dirichlet boundary data corresponding to the sum of real constant values rho plus some small Dirichlet data. So this is a situation in which we consider this problem. And the first thing that I would like to say is that this equation is nonlinear. So the nonlinearity will come from the fact that this conductivity depends on the solution. But beside that, we will try to consider a rather general behavior of this type of conductivity with respect to the solution of the equation. So in this context, we can state our inverse problems, which will be a uniqueness result. You can refer to what I have said in terms of uniqueness. So we will consider some observation through which we will try to state some injectivity properties. And the observation or measurement that we will consider here can be considered as follows. So here the idea is to apply voltage at the boundary of our open set, the voltage being given by this Dirichlet data corresponding to the sum of the constant function plus some small Dirichlet data. And to each of these voltage, we associate the measurement of the current flux, which will be given by the normal derivative of the solution of this boundary value problem weighted by the conductivity. And the idea will be to consider in terms of observation or measurement, different type of voltage of this type that we apply at the boundary, and a different type of measurement of the current flux, each of them associated to the different voltage that we apply. And from this type of information, we want to determine what will be the unknown in the system and which will be given by this conductivity, which will have simultaneous dependency with respect to the space variable, the solution, and the gradient of the solution. So this is the inverse problem that we consider here. So let me first say a few words about these inverse problems. And let me first say that this inverse problem is strongly connected into actually a nonlinear formulation of the so-called Calderón problem, whose first formulation goes back to the seminal work of Calderón of 1980, and for which the first positive answer was given by Sylvester and Uhlmann in 1987. So let me recall the Calderón problem in its initial formulation. So in its initial formulation, the Calderón problem can be considered through a boundary value problem similar to the one that we have considered, except that this time the conductivity have no dependency with respect to the solution, which make this equation linear. So for this linear equation, the idea of the Calderón problem is to consider a problem with observation that can be stated as follows. So we apply different type of voltage at the boundary of our open set, voltage being given by the Dirichlet data. And to each of these voltage, we associate the normal derivative of the solution of this boundary value problem weighted by the conductivity. And the idea will be to consider in terms of observation, what will be encoded for this different type of voltage and measurement of the current flux into what we call the Dirichlet to Neumann map, which is the map that sends each voltage to the measurement of the associated current flux. And from this Dirichlet to Neumann map, the goal is to determine the conductivity appearing in the equation. So this is the formulation, the initial formulation of this Calderón problem. And now our goal is to extend this into a nonlinear framework, that is nonlinear equation, and to try to determine more general class of conductivity that depends also on the solution of the equation. So concerning the physical motivations of our problem, the first physical motivation that we can mention for our problem are those of the classical Calderón problem and its connection to the so-called electrical impedance tomography with application in geophysical prospection or medical imaging. But beside that, the nonlinear model that we consider have its own applications in the field of different models, including models of dielectrics, plastic modeling, electroradiological, and thermoradiological, as well as several others. So here, the problem that we are interested in can be stated as follows. We want to consider a class of nonlinear conductivity having three classes of dependency. So the first dependency will be the dependency with respect to the space variable. The second one, the dependency with respect to the solution. And the last one, the dependency with respect to the gradient of the solution. So to explain this in a more physical framework, let me state it that way. We have here excitation and measurement, which are given by the voltage and the measurement of the current flux that we apply on the accessible part of the system. So this accessible part of the system can be seen as the boundary of our open set. And the goal is to determine properties about nonlinear conductivity that admits variation inside the system, that is on the open set omega, independently of the solution of the equation, which is given here by the dependency of this conductivity with respect to the space variable, in addition to this his dependency with respect to the solution of the equation. So here we apply voltage and make measurement of the current flux on this accessible part of the system in order to determine some properties that admits variation on the inaccessible part of the system. So this notion of accessible part of the system and inaccessible part of the system appears in many applications of inverse problems, including problems of medical imaging, where the accessible part of the system corresponds to the body surface, the part where you can apply excitation and make measurement. And the goal is to determine what happened inside the body, which corresponds to the inaccessible part of the system. So this is how we can physically justify the formulation of our problem. Now, let me say also that there is some mathematical motivations in the study of this type of problem, coming first from the high nonlinearity and ill-posedness of this problem. So what I would like to say is that in its initial formulation, that is its formulation for linear equation, the Calderón problem is already a nonlinear problem. So here we add nonlinearity to this nonlinear problem by trying to determine some more general class of conductivity, which have, in addition to the dependency with respect to the space variable, have also the dependency with respect to the solution of the equation. Beside that, you can also see the problem that we consider, the natural extension of what has been considered for linear equation, namely the fact that we add to the dependency with respect to the space variable of this problem stated for linear equation, some additional dependency with respect to the solution of the equation, which makes this problem a natural extension into the nonlinear framework of what has been considered so far for linear equation. Finally, what I would like to mention is that the problem that we are considering here, that is the determination of conductivity combining these three classes of dependency, correspond to an open problem whose study started with the work of Sun and Uhlmann in 1997. Okay, so this is what I wanted to say in terms of motivation. Now, let me go back to the position of our problem and state things in a little more clear way. So here we consider, as I said, this boundary value problem with our nonlinear equation and the voltage that we apply at the boundary of our open set associated with this type of Dirichlet data. The first assumption that we make are assumptions related to the forward problem. I will say a little later on more about that, but the idea is to deal with sufficiently smooth solution of this problem, and we need to consider a framework which allows the well-posedness of this boundary value problem. So this will be done first by making some regularity, imposing some regularity assumption to the nonlinear conductivity that we consider here. Positivity assumption also, we need also a condition on the sign to make, in order to make this equation being elliptic. And after that, the idea will be to consider a sufficiently small Dirichlet data in such a way that for all constant, this problem will be well posed and that we will have sufficiently smooth solution of this boundary value problem. So the proof of this well-posedness of the boundary value problem, provided that you have access to sufficiently small Dirichlet data, can be proved actually with an easy application of the implicit function theorem. The idea is that constant function are actually solution of this equation due to the fact that you have a gradient first here. So provided that you choose this Dirichlet data f to be sufficiently small, thanks to the implicit function theorem, you can show that actually this problem will be well posed. It will be well posed and you will have access to a sufficiently smooth solution of the problem 3. And thanks to that, you can define the Dirichlet to Neumann map, which will send any Dirichlet data of this form, that is constant function plus small data, and it will send each of this type of voltage or Dirichlet data to the normal derivative of the solution of this boundary value problem, dt by the conductivity. So this is the context in which we consider our problem. And now we can state our inverse problems as follows. we want to determine some class of conductivity combining these three classes of dependency: space variable, solution which will be associated with the variable rho, and gradient of the solution which will be associated with the variable psi. And what we want to determine is this class of function from the knowledge of the Dirichlet-Neumann map on this type of Dirichlet data, which can be seen as the knowledge of this Dirichlet-Neumann map on some neighborhood of constant function. This is the class of data that we consider here and the class of parameter that we want to determine from this type of data. Before moving to the statement of our problem, let me say a few words about what is known so far for this class of inverse problems. And I will try to make a general introduction to this class of inverse problems, which are not always well known. And the first thing that I would like to say is that the determination of nonlinear terms appearing in partial differential equations, and mainly here elliptic equations, can be divided into two categories. The first category is somehow the historical one, the one for which authors started to study this class of problem, correspond to the idea that the behavior with respect to the solution of the equation for this nonlinear term is part of the unknown. So it is not known, and you try to determine it in some general framework. The second category in this class of inverse problems is a little different in a sense that you make some assumption to the nonlinear term under consideration in terms of their behavior with respect to the solution, by assuming that the behavior with respect to the variable associated with the solution of this class of nonlinear term is of polynomial type or it is holomorphic. Here in the second category, the idea is to use this nonlinear interaction, which can be applied as far as I know only for this specific class of nonlinear term, in order to make some improvement of what is known for linear equation. So here we will focus our attention in inverse problem in the first category. However, I would like to mention quickly a few results that can be associated with this class of inverse problems, but in the second category. This includes, for instance, the work of Feizmohammadi, Oxalen, Krupchyk, Uhlmann, Lassas, Lematainen, Lin, and Salo. So from now on, I will describe only results in the first category. So I will start with the determination of semilinear term. So here, yes, the title is missing. Anyway, so I will start with the determination of semilinear term. So here we have an elliptic equation with a semilinear term. And the idea will be, in a similar way to the problem that we are interested, to try to determine this semilinear term, which have dependency with respect to the space variable and the solution of the equation from the associated Dirichlet-Neumann map. So here, this result has been considered in the continuity of the initial work of Isakov, who have introduced this idea of linearization in 1993. And this linearization idea was applied for parabolic equation initially. And in the continuity of this work, Isakov-Sylvester and Isakov-Nachman, so Isakov-Sylvester treated this problem for dimension of space higher than 3. Isakov-Nachman, in the case of dimension n equal to 2, treated the problem of determining this class of semilinear term from the knowledge of the associated Dirichlet-Neumann map. So here, actually, one of the issues for this problem is that you have no control. So you want to determine some unknown parameter that depends on the solution, but you have no control of what happened to this class of solution inside the open set. Since you don't know this nonlinear term, you cannot have access, you cannot have control of this solution. You have only control of this solution on the boundary of the open set through the Dirichlet data that you control. And since you do not have this control, these authors need to make some strong assumption on the behavior of this class of semilinear term by assuming that the behavior of this class of semilinear term is uniformly Lipschitz with respect to the variable associated with the solution. And by means of this assumption, they managed to prove the full recovery of this type of semilinear term from the knowledge of the associated Dirichlet-Neumann map. So this is the first result that we can mention in terms of one of the first results, not the first one, but one of the first results that we can mention in terms of determination of nonlinear term appearing in elliptic equation, a result which has been extended a little later on First by Isakov in 2001, where Isakov treated the case of semilinear term depending this time only on the solution. So here you have still a semilinear equation that you try to determine from the Dirichlet-Uhlmann map. But in addition to that, so this restriction allows Isakov to consider data not given by the full knowledge of the Dirichlet-Uhlmann map, but some partial knowledge of this Dirichlet-Uhlmann map by restricting the voltage that we apply to some arbitrary open subset of the boundary. This is done by the fact that the Dirichlet data that you consider here have a support which is contained on this arbitrary subset, open subset of the boundary, and by measuring the current flux also on this arbitrary, on the same arbitrary subset of the boundary. With this type of assumption, Isakov proved in 2001 the unique recovery of semilinear term depending only on the solution. So here I would like to mention also that I have obtained similar result for hyperbolic equation. In 2001, so still in 2001, but maybe not at the same time because it's different type of journal, Isakov treated the case of semilinear term having simultaneous dependency with respect to the solution and the gradient of the solution in the case of dimension of space n equal to 3. So here we can see what I wanted to recall quickly. This is not an exhaustive list, but at least it will give you an idea of what has been done so far initially for semilinear terms. Now let us move to quasi-linear terms. Let us move to the determination of quasi-linear terms appearing in quasi-linear elliptic equation. So from now on, we will consider equation of this form, that is the divergence of capital J, where capital J is a vector valued function, depending on the space variable, the solution, and on the gradient of the solution. So here our equation will be divergence of capital J is equal to 0. And the idea will be to try to determine the unknown parameter appearing in this class of equation by means of the knowledge of the associated Dirichlet-Uhlmann map, which can be defined in this context as follows. So here, for this class of problem, I would like to first mention the work of Sun of 1996, who have treated the determination of a conductivity similar to the one that we consider, except that here Sun considered a conductivity depending only on the space variable and on the solution. Here there is no dependency with respect to the gradient of the solution. In 1997, Sun and Uhlmann extended this initial work of Sun by considering a more general second order nonlinear term, which will be matrix valued. This time, this one is real valued, this one is matrix valued, depending still only on the space variable and on the solution of the equation. And this problem was considered by these authors in the specific case of dimension n equal to 2, or in the case where this type of nonlinear term is analytic with respect to the space variable and with respect to the solution of the equation. A little later on in dimension n equal to 2, so this is a result restricted to dimension of space n equal to 2, Harvas and Sun considered the determination of a general second order nonlinear term depending on the space variable and on the gradient of the solution. So here we have mentioned result dealing with conductivity depending either on the solution or on the gradient of the solution, or even more general second order term, nonlinear term that depend on the space variable and on the solution, or on the space variable and on the gradient of the solution. For results dealing with determination of this class of conductivity or second order nonlinear term depending on the solution and on the gradient of the solution, one can refer first to the work of Shankar, but also to the work of Munoz and Uhlmann, who have treated the determination of this class of nonlinear conductivity. But in contrast to what we want to consider here, there is no space dependency. You need to get rid of the space dependency in this work. Finally, I would like to mention our more recent work with Krupchyk and Uhlmann, where we have treated the determination of conductivity depending on the space variable, the solution, and the derivative only in one direction of the solution. So here we do not have full dependency with respect to the gradient of the solution. However, in this work, we manage, in contrast to the work that I will present a little later on, to restrict the measurement of the current flux in an arbitrary open subset of the boundary, and to restrict also the voltage that we apply to this same arbitrary open subset of the boundary. So what we can say...
Can I ask you a question, if you don't mind? Hi, this is Sivaguru here.
Yes.
So I had this question earlier on also when you're talking about the arbitrary open subset of the boundary.
Yes.
So do you have to take all possible small subsets, or you just fix a set and then you make all the, you provide all the voltages just in that subset and you can recover the full information about the equation?
Yes, so the subset is chosen arbitrary. And
But it's fixed.
apply...
You don't have to. We don't have to consider different subsets.
No, just one subset. You fix arbitrary open subset. You apply all the voltage on this subset and make the measurement of the. But you need to make measurement of the current flux on the same subset. So this is
okay. All right. Yeah.
a restriction on it.
Thanks.
Okay, so what is unknown here and what has not been proved so far is the determination of a conductivity, as I said, combining this three class of dependency, that is dependency with respect to the space variable, the solution, and the gradient of the solution. And this is what we want to consider here. So let me go back to the statement of our problem and recall it a little quickly before we move to the statement of our result. So we have here our quasi-linear equation, the voltage that we apply with constant function plus small Dirichlet data in order to guarantee the well-posedness of this boundary value problem. After that, we associate this boundary value problem the following Dirichlet to Neumann map. And our goal, as I said, is to determine some class of conductivity combining these three classes of dependency. And here I will now state our results. So I will state two results. A first one, which can be stated as follows. So here we pick the constant function rho appearing here to be equal to 0. And we try to determine information about this class of conductivity while this constant function is fixed at 0. This means that we consider the Dirichlet to Neumann map on some neighborhood of 0 with small Dirichlet data, if you prefer. So here we make some assumption mainly related to the forward problem that we fix at rho equal to 0. So the variable associated with the solution of the equation is fixed at 0, and the one also with the gradient with respect to the gradient of the solution in such a way that we have these positivity properties. To this, we add some smoothness properties. And thanks to that, we can state our first result, which can be stated as follows for these two classes of conductivity of index 1 and 2. So if the Dirichlet to Neumann map for these two classes of conductivities coincide for small Dirichlet data, what we can say is that all possible order of differentiation of this conductivity with respect to the variable associated with the solution of the equation and the variable associated with the gradient of the equation fixed at rho equal to 0 and psi equal to 0, but x lying on our open set coincide for these two conductivities. So this result somehow say that if you consider here conductivity that will have dependency with respect to the variable rho and psi holomorphic, from this type of property, you can get the full recovery of this type of conductivity. We recover here the Taylor coefficient of this type of conductivity. So now let us see what happens if we improve our data, which means that we consider the knowledge of the Dirichlet to Neumann map on the neighborhood of all constant functions. So here again, we pick two classes of conductivities. We assume that we have some properties. So this time we need to consider properties for all possible values of the variable associated with the solution of the equation. And in addition to that, since this time we want to deal with the full recovery of this type of conductivity, we add some analyticity properties to this conductivity with respect to the variable psi, where psi here will be the variable associated with the gradient of the solution. And here, what we show is that if the Dirichlet to Neumann map for these two classes of conductivities coincide on this type of neighborhood of constant functions, then the two conductivities fully coincide. And so the full recovery, again, is due to the fact that we have this analyticity variable, analyticity with respect to this variable psi. In some sense, we determine something similar to here in the sense that we have all possible derivatives with respect to this variable psi fixed at psi equal to 0, which means that we recover the Taylor coefficient of this type of conductivity with respect to this variable psi. So this is the two results that we have obtained. Now, let me make a few comments about this result. So the first comment that I would like to say is that here we give the first positive answer to this Calderón problem, stated for this class of nonlinear conductivity, combining this three class of dependency, that is dependency with respect to the space variable, the solution, and the gradient of the solution. So the class of nonlinear conductivity that we consider are subjected to this condition A1, A2, and B1, B2, which, as you can see, are mainly related to the forward problem, to which we add this analyticity property with respect to this variable psi for the full determination of the conductivity. So here, the class of conductivity that we consider, combining these three classes of dependency, can be seen as a combination of what has been considered by Sun in 1996 and Harvas and Sun in 2002, and which will consist in some class of fully quasi-linear conductivities. Concerning the proof of this result, so I will give the detail a little later on, but one of the important ideas is this idea of multiple order linearization. So as I said before, this idea of linearization goes back to the work of Isakov of 1993. Here, Isakov considered the first order linearization. This idea of first order linearization of Isakov has been extended by Sun and Uhlmann in 1997, where these authors considered the second order linearization. And then after that, a long time after that, Kurilev, Lassas, and Uhlmann exploited this idea of infinite order linearization. So this idea of linearization that we will see a little later on can be seen as the idea of trying to get information about a function by taking a look at the derivative. So in that sense, Isakov considered the first derivative, and he tried to get information about this function from its first derivative, while these authors extended this approach to all possible derivatives in order to get information about the function. And the idea actually is something that we will exploit here, is the idea of trying to exploit this infinite order linearization in order to get as much information as possible for this class of conductivity. So here, this idea of infinite order linearization has been used by Kurilev, Lassas, and Uhlmann in a different context for some class of nonlinear hyperbolic equation. So in that sense, we consider here things a little differently than these authors. Okay, so now let me give you an idea of the proof of this result, and I will focus my attention on this idea of linearization, which is somehow the easiest part of this result that I can present, and somehow it will explain this idea of how we can deal with the determination of nonlinear term, or at least how it was done by most authors so far. So in order to understand this idea of linearization, let us speak. So I will consider here the situation for term 2. Sorry, just quickly recall you. Term 2, we have this type of properties, and we want to fully determine this class of conductivities. So we are in the situation of term 2. So we start by considering the following boundary value problem with Dirichlet data corresponding to the sum of this constant function, plus some Dirichlet data, small Dirichlet data that we consider in such a way that this problem will be well posed for all possible values of epsilon between -1 and 1. So we add here this parameter epsilon. And we consider this boundary value problem for the two different conductivities appearing in our theorem. This index k is the index of the conductivity. And we will have a solution of this boundary value problem combining the index of the conductivity, the index k, plus its dependency with respect to this parameter epsilon appearing in this Dirichlet data. So now the idea of this first order linearization is to apply a differentiation to this solution with respect to this parameter epsilon and to take the value of epsilon at 0. By proceeding that way, this is actually in some sense a Frechet derivative that we apply to our problem, but we have stated a little easier way than this idea of Frechet derivative. By proceeding to this differentiation, what we get is a function vk, which will be actually solution of a linear problem. So this linear problem can be described as follows. We have here a conductivity which corresponds to our nonlinear conductivity that we take at x, and with respect to the variable associated with the solution at rho, and finally with respect to the variable associated with the gradient of the solution at 0. So here the idea actually can be explained in a little different way. We linearize around constant functions. And this idea goes back to the approach that has been already considered by Sun. So Sun considered this idea of linearizing along constant function. And what we exploit here again is the fact that constant function are actually solution of these equations. And thanks to that, we obtain through this first order linearization a solution of this linear problem. And now the idea is as follows. We have proceeded to this linearization, and we can make use of this linearization in order to first recover the Dirichlet-Uhlmann map associated with this linear problem. So here we consider the Dirichlet-Uhlmann map associated with this linear problem, and this as corresponding conductivity that appears here. So it sends each voltage to the measurement of the current flux for this linear problem. And what we can show is that the values of this linear Dirichlet-Uhlmann map at this Dirichlet data H will be given by the differentiation with respect to the epsilon of the Dirichlet-Uhlmann map associated with the nonlinear equation that we take at Dirichlet data of the form rho plus epsilon H, and this for epsilon equal to 0. And now the idea will be to use the fact that actually we know our Dirichlet-Uhlmann map on the neighborhood of constant functions. And provided that we have this, we can show that actually we can recover the Dirichlet-Uhlmann map for the linear problem, and this for the two conductivities of index 1 and 2. This is what we get. And actually we can recover this linear Dirichlet-Uhlmann map for small data. But what we can exploit here is that actually this Dirichlet-Uhlmann map or linear map. So using the linearity of this map, we can fully recover the Dirichlet-Uhlmann map here. And thanks to that, we are in position to apply the result of Sylvester and Uhlmann in order to get the full recovery of this type of conductivity. So here the conductivity are recovered for the space variable lying in the open set omega, the variable associated with the solution of the equation lying on R, but the variable associated with the gradient of the solution is fixed at 0. And this is actually what we get from this first order linearization, which has been considered already by many authors, including Sun. And now the idea is to go further, and in order to get more information about this class of conductivity with respect to their behavior on with respect to this variable associated with the gradient of the solution. And this is why we need to go further here than this first order linearization. And this is what we will do. For that, and from now on, we assume that these two conductivities, gamma 1 and gamma 2, for psi fixed at 0, will be denoted by gamma 0. And now we'll proceed to the higher order linearization. So this higher order linearization, I will describe it through some iteration process. So I will fix for that m to be an integer. And I will consider a more general context for this linearization procedure, while this time the Dirichlet data takes the form of the sum from L equal to 1 to m of epsilon L times HL. So here HL will be some small data, and epsilon 1 to epsilon m will be some small parameters that we combine into a vector valued parameters epsilon, whose coordinate will be given by epsilon 1 to epsilon m. And we will obtain here, again, for these two classes of nonlinear conductivity, a solution of this boundary value problem. And what we want to consider this time is the composition of differentiation with respect to epsilon 1 to epsilon m of the solution of this boundary value problem that we take for the vector epsilon equal to 0. And what this process leads us is to the solution Vk, Wk of the following boundary value problem. So we have here a boundary value problem with the conductivity gamma 0, which is the one that we have already recovered in the first order linearization. And what will distinguish these two solutions of this boundary value problem is what happened in the source term of this boundary value problem. So this source term is the expression that gives us this index k. And the information that we want to determine about our nonlinear conductivity is contained into this source term. This is the part that we want to recover. And again, we will use here the idea that we can have access to the normal derivative of the solution of this boundary value problem at the boundary by considering the composition of differentiation with respect to epsilon1 to epsilon m of our Dirichlet to Neumann map considered for the nonlinear problem that we take at Dirichlet data of this form, and this for the vector epsilon. So I recall that epsilon is this vector fixed at 0. And again, combining this with the fact that we have a knowledge of our Dirichlet to Neumann map on the neighborhood of constant function, we can state that the normal derivative of W1 coincides with the normal derivative of W2. So once we prove that, we will proceed to an iteration arguments. So here we assume that we know all the differentiation with respect to psi at the order k, from k going to 0 to m minus 1 of the two quasi-linear conductivities gamma 1 and gamma 2 at psi equals to 0. And assuming that this properties is fulfilled, we fix gamma to be the difference of gamma 1 and gamma 2. And by proceeding in some arguments that I will not describe here, some technical argument that I will not describe here, we are left with this type of identity, saying that the differentiation with respect to psi at order m of our conductivity gamma, considered at psi equal to 0, which will be a symmetric tensor of rank m, applied to this type of function. So here, the function u of index j will be some arbitrary solution of these linear elliptic equations, and to which we consider the following additional term, and for which we take the sum for all possible permutation of the set 1 to m plus 1, and that we integrate all of this, we will have a quantity that will be equal to 0. And here the idea will be to exploit the fact that this identity holds true for all possible solutions of this elliptic equation. Using that, we will try to recover this differentiation with respect to psi at the order m, which will be given actually into a linearized problem that can be stated as follows. So this linearized problem corresponds to the determination of a function taking values in symmetric tensor of rank m. So here we assume that we have an identity comparable to the one that we consider here for capital T, which will be a symmetric function taking values into symmetric tensor of rank m. And this for all possible solutions of this linear elliptic equation. And provided that we have this type of identity, our tensor valued function will be uniformly vanishing on omega. Once we have this result, we can apply it into our context. So we fix our symmetric tensor to be equal to the differentiation with respect to psi of our conductivity that we take at psi equal to 0. So here, gamma, I recall it, gamma is a difference of the two conductivity. And thanks to this property, we can show that this tensor will be uniformly equals to 0, which means that the differentiation with respect to psi of the two different conductivity coincide when psi is fixed at 0. And by an iteration argument, the iteration that we have considered before, we can show that this identity holds true for all integer m. And combining this with the analyticity of our conductivity with respect to variable psi, we can get from these last properties the full recovery of our conductivity, that is gamma 1 equal to gamma 2 as it was stated in theorem 2. So now let me say a few words about these linearized properties and how we get these linearized properties stated in proposition 1. So for these linearized properties, we need to combine two classes of arguments. The first one is a Runge type of result, where we show that these sets corresponding to the scalar product of the gradient of two solutions of this elliptic equation weighted by the conductivity is dense in the sense of L2 of omega. And the second one is the use of some specific solution of this type of linear elliptic equation that are called complex geometric optic solutions. So here we consider some specific class of complex geometric optic solutions whose product concentrate near lines having some specific direction but passing through any point of our open set omega. So here the construction of this type of complex geometric optic solution is inspired by what has been considered before by Greenleaf and Uhlmann. So here is what I wanted to say about our results. Now, let me complete this talk by a few prospects that I would like to describe here. And I will start with a prospect related to semilinear elliptic equation and the determination of semilinear term for semilinear elliptic equation. So this first prospect is it goes in the direction of what has been considered by Isakov-Sylvester and Isakov-Nachman in their work of 94 and 95. And the idea will be to consider a semilinear elliptic equation and to try to determine the semilinear term having simultaneous dependency with respect to the space variable and the solution of the equation from the knowledge of the associated Dirichlet to Neumann map. So here the goal actually will be to try to extend what has been considered by this author, whose analysis was restricted to semilinear term whose behavior with respect to the solution is uniformly Lipschitz. And here our goal will be to try to make an improvement in terms of generality of the class of nonlinear term under consideration for this problem. For this result, who in terms of generality has been unchanged for something like 26 years. But this is a first direction that I would like to present here in terms of determination of nonlinear term for elliptic equation. The second prospect that I would like to talk here is a little different in a sense that this time we will not try to extend in terms of generality the class of nonlinear term that we want to consider, but to restrict this class, but try to get some better result than just the uniqueness. So here we consider this class of quasi-linear elliptic equation with nonlinear term, which this time have only dependency with respect to the solution of the equation. And the idea will be to try to determine this type of nonlinear term, quasi-linear for this one and the semilinear here, from the knowledge of the associated Dirichlet to Neumann map of, sorry, charge, it's okay, sorry. The determination of these two classes of nonlinear term from the associated Dirichlet to Neumann map. And here, due to the fact that we managed to restrict the class of nonlinear term to nonlinear term depending only on the solution, we would like to consider not the full knowledge of the Dirichlet to Neumann map on the full boundary, but to restrict the measurement of the current flux and the class of voltage that we apply to some arbitrary subset of the boundary. And in addition to that, we would like not just to get a uniqueness result, but to take a look to stability result. So the stability result corresponds to the second meaning that I have given to this word determine. And the idea of having stability would be actually to try to have a good stability result, not a logarithmic one, but a Holder one. And this Holder stability will allow us to move further to possible numerical reconstruction of this class of parameters. So this is the second prospect that I wanted to talk about. And finally, the last prospect that I would like to talk about is actually a prospect that for which we have already a result. So this time we consider a problem associated with this class of quasi-linear parabolic equations. So here we have an equation that depend on the time variable, for the time variable lying on an interval of the form 0 capital T. So space variable lying on an open set omega. And we consider this type of quasi-linear parabolic equation with a conductivity which depend on the space variable, the time variable, and the solution of the equation, and a first order term that are called convection term, depending on the space variable, the time variable, the solution, and the gradient with respect to the space variable of the solution. So here, this type of equation can be seen as some nonlinear Fokker-Planck equations, but also some nonlinear convection diffusion equations. And in addition to that, some generalized formulation of the Burger's equation. And here the idea will be to associate with this equation the following initial boundary value problem by fixing the initial value at constant functions and considering Dirichlet data corresponding to the sum of a constant function and some small Dirichlet data. After that, we define the following map that send each kind of source that we apply, a source of diffusion that we apply at the boundary of our open set times this along this interval of time 0 capital T, and to associate with this each of these source the measurement of the flux, which will be given by the normal derivative of the solution of this initial boundary value problem weighted by the conductivity. So here in this context, we would like to treat the problem of determining simultaneously the nonlinear conductivity and the convection term, which are actually important physical quantities in the context of the different problem that I have described. Here you have, for instance, the diffusive terms, while in this second nonlinear term, you have the velocity field of the moving quantities, which are important quantities for this class of nonlinear equation. And this from the knowledge of this map for all possible values lambda in a first step, and then for lambda equal to 0, that is this constant values for the initial condition fixed at 0. So what we would like to say is that actually we have already a result. It appears this morning on arXiv with Ali Feizmohammadi and Gunther Uhlmann in that direction. Okay, thank you for your attention.
Let's thank the speaker for his wonderful talk.
Thank you.
Does the audience have questions for the speaker?
So I have a question.
Yes.
So what about for matrix conductivities? Can we do something? The thing is, if it is depending either semilinearly or quasi-linearly, can we recover all the coefficients?
So this has been already somehow treated in the work of, but not with the dependency with respect to the gradient. This is what has been done here by Sun and Uhlmann. So this matrix valued is somehow the metric case. And it was also done by Harvas and Sun here. So, but
sure. But the thing is, but in your general setup,
so in our general setup, I think it would become a little more complicated. And moreover, what you need in our setup, and this is something that was needed also here, is the result for the linear problem. So for the linear problem, this determination of metric has only been done in dimension 2, or provided that you have analyticity assumption. So I think something could be done in this specific setting of dimension 2, but we have not tried. But of course, I think something can be done. But the problem would become really difficult if you start to think of a metric. Actually, even here, in this second problem that you can see, so we have stated for parabolic equation, but you can also think of it for elliptic equation. Even for a convection term, we need to fix the direction. So we have a real valued function times a direction which is somehow fixed. We cannot add this dependency with respect to the gradient of the solution in this vector direction. Things will become really complicated if you do that. So for a metric is even worse.
I see. And the other thing is the partial data problems. So I suppose, in your theorems 1 and 2 that you described, you did this for the full data. Is that correct?
Yes. Full bundle.
What about, so the thing is, then, if it's partial data and with the same, the support of the Dirichlet and the Nyman is also measured on the same open subset, the corresponding linear result is missing. So I suppose there is the same obstruction. Is that correct?
Yes. So what can be done here in that direction? This is what we have done with Krupchyk and Uhlmann. We made some assumption on this class of nonlinear term in order to be able to proceed to this partial data result. So we use in this result the nonlinear interaction, actually. So
I see.
We use it. So if you don't use this nonlinear interaction, as you said, the linear problem is open, so there's no hope to treat it for the nonlinear one.
I see. Okay, yeah, thanks. Very nice talk. Thank you.
Thank you very much.
Yeah, hi, I have a question. So,
hello.
Hi, Kian, this is Manmohan here.
Hello.
Yeah. Hello.
Hello. How are you?
Yeah, I'm fine. How are you?
I'm fine, thank you.
Yeah. So in this you mentioned this JX, this is omega dot gradient. So this omega also you are varying, or this is just a fixed vector?
Omega. Yeah. No, omega is fixed direction. The idea is that we have the derivative in one fixed direction, arbitrary one. This is why we have introduced this omega. But think of it as a first derivative, the derivative dx1. Think of it as dx1. Be easier.
Okay.
In some sense, the dependency with respect to the gradient need to be real valued. This is the idea.
I see. Okay.
Not vector value.
I see. And this gamma is scalar.
Gamma. Oh, the gamma is the
just,
conductivity. Is the
which is scalar one.
Yes, scalar. Yes, scalar. Of course, scalar,
Okay.
scalar.
Okay.
Not vector value.
Okay. Oh, this one has not appeared on archive yet.
Yeah, no, it is on archive.
It is on archive. Okay. Okay.
It is on archive.
Okay. 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 Thank you. Yeah. Okay. Thank you.
Thank you. Welcome.
Yeah.
Hi, I have a question actually.
Yes.
What type of nonlinearity you are considering? I mean, is it kind of P-Laplace type nonlinearity here, or
it can include, I think, some class of P-Laplacian. It is in the physical motivation that I mentioned here. There is some P-Laplacian things. It can.
Yeah, no, I mean your problem that gamma, is it kind of P-Laplace type or maybe a different type of nonlinearity? What kind of assumptions you're considering?
Here it's general type of nonlinearity. We do not make a clear assumption about it, but at some point I think it can include some class of P-Laplacian also.
Okay, I see. Okay, yeah, thanks.
So I had a kind of probably a basic question. I don't work in inverse problems, so if you would sort of bear with me. So from what I understand, all of this is done around the constant functions, right? You do apply some kind of perturbation to the constant function, and then you apply some technical stuff to get things working. So could you do this around some other fixed function or some other class of functions? Could this implicit function theorem approach be done?
So the idea is that why, so you need to know why we use a constant function in order to see what will be the restriction on what you're saying. The idea is that constant function or solution of this equation independently of the choice of the conductivity. This is what we need here. And
so that doesn't place any restriction on gamma.
Yes, no, you can choose any gamma that you want. Constant function will be solution of this equation. If we manage to have function of this type, yes, of course, we can do what you are mentioning. But if you don't have knowledge of this conductivity, except constant function, I cannot see what class of function you can have in terms of solution of this equation. This is why we use constant function, actually.
So just sort of a small follow-up. So suppose you knew one solution, right? Say U0.
Okay.
Could you do this machinery around U0? Does that make sense? Or
I think yes, it would. So, but the idea is that okay, you have U0, but you can also get the recovery of your conductivity with respect to the variable associated with the solution only with this U0.
I see. Okay. Yeah.
This is the other point.
Right. Yeah.
There's 2 points.
Sure. Yeah. Thank you very much.
You're welcome.
Are there further questions from the audience? Let's thank the speaker for.
Thank you very much for the invitation
and for the interaction.
Thank you.
Thank you. It was a pleasure.
Thanks, Yavar, and hope to see you soon.
I hope also.